When straight water waves pass through the gap in the harbour walls, we notice they become curved and spread into the region behind the walls. This effect is due to diffraction. Diffraction occurs in all types of waves which are incident on an aperture or obstacle of similar size to the wavelength. Click on the laser. When light from a point source passes through a small circular aperture, the image form is not a bright dot, but rather a diffuse circular disk known as Airy's disk, surrounded by much fainter concentric circular rings. This is an example of diffraction. Diffraction is of great importance because the eye and many optical instruments have circular apertures. The reason for the formation of the dark and bright circular rings will be explained during the lesson. When an object such as a razor blade is placed in front of a light source, you might expect to see a shadow with sharp edges. Instead, diffraction causes a blurring effect on the edges with a series of bright and dark lines following the shape of the internal and external edges. Click the Light Source button. Introduction to Single Slit Diffraction. In this lesson, you will learn the single slit diffraction pattern. To derive and use the formula sin theta equals lambda over A for the first minimum in the diffraction pattern for the single slit. About the intensity of the fringes. Use the slider to vary the width of the gap. What effect does this have on the wavefronts after passing the gap? Answer: a narrow gap causes more spreading and produces circular wavefronts. A wide gap causes less spreading and produces wavefronts that are straight in the center and curved at the ends. When the width of the gap is approximately equal to the wavelength, diffraction and spreading are maximized. When light is incident on an aperture of width comparable to its wavelength, diffraction causes the light to spread out as it passes through the aperture. As you have learned in the previous lesson, this can be explained in terms of Huygens theory, in which each point along a wavefront is considered to be a secondary source. The new wavefront is then constructed along the tangent of these secondary waves. Click the Screen button. When a screen is placed behind the aperture, we notice that a distinctive pattern of bright and dark fringes is formed. These are known as maxima and minima. There is a wide, bright maxima at the center surrounded on either side by alternate dark and bright fringes. The maxima becomes less bright further from the center. Click the Intensity button to see a graphical representation of how the brightness varies. What do you observe? Answer: the intensity at the center of the central maximum is greatest, and it decreases rapidly to zero at the first minima. Secondary maxima of much lower intensity are also observed. Now vary the aperture width using the slider. What do you observe? Answer: decreasing the aperture increases the width of the central maximum and the distance between maxima. Use the slider to investigate the effect of wavelength on the diffraction pattern. What do you observe? Answer: increasing the wavelength increases the width of the central maximum. The fact that the diffraction is dependent on wavelength gives rise to many optical phenomena. This photograph shows a halo around the sun, which is formed by diffraction of sunlight due to many uniform ice crystals in the atmosphere. Notice that the halo is comprised of a spectrum of colors. This is because sunlight is a mixture of light of different wavelengths or colors. When light diffracts around the uniform ice crystals, the colors separate slightly according to their wavelength. Summary: the formation of a single slit diffraction pattern depends on the width of the slit, the wavelength of the light. The diffraction pattern is formed only when the width of the slit is of the same order as the wavelength of the light.